Yeah, camera on everyone. Let's start off. Yeah, others keep your camera on. So, as we have finished with oscillations, SHM. Quite an important chapter. So, do make sure to start solving. Great. So, we'll be starting off with electrostatics today. Like I discussed last time, this entire electromagnetism chunk is a pretty high weightage. See, till now, whatever we did in mechanics is all one thing, but this entire electromagnetism is around 33% weightage. Means literally 1/3 of physics marks are going to come from this entire one section of electromagnetism. And frankly speaking, I feel it is a little easier than mechanics. Right. The only issue is, unlike mechanics, where I say the body is rolling, body is going up, you can visualize. It becomes a little difficult to visualize electric fields and magnetic fields. So we will see what can be done about that. We will try to see as many different demonstrations as possible. Right. Yeah, we'll just keep your cam on. Ahana, cam on. Daksha, others, keep your cams on. So let's start off. Like I keep saying, don't worry about writing the notes. You'll get the PDF. So focus on listening, understand the concepts, do all the problems. Anything you're not clear, don't hesitate to ask. You can always unmute and ask your doubts, or you can always type in the chat box here to the co-host. So what's electrostatics? In the word only, you can see there is something called statics there. So it deals with interaction between charges. Charges at rest or slow moving charges. Okay, the word, if you look at it right, it's a slow moving charges. So when it's a slow moving charges, we're looking at speeds which are much less than speed of light. So the particles start going pretty fast, things start getting messed up. We'll see what things can get messed up. And also we neglect any magnetic and relativistic effects. So a moving charge not only creates electric field, it also creates something called magnetic field. We don't want to deal with that right now. So we neglect any magnetic and relativistic effects. Relativistic is one, what if when you get pretty close to the speed of light, or when you're actually moving, mass increases, time decreases, length changes. So a lot of these things actually happen. And that's all the Einstein relativity thing. We'll not get into that part. So we have a part for that. It's called quantum electrodynamics. So when you're actually doing MSc physics, that's what you learn. But anyways, for it is at least our level, we'll keep the things simple. We are only doing slow moving charges. Even if you're going at a speed of 10,000 kilometers per hour, it is slow only because speed of light is 3 lakh kilometers per second. Correct? So compared to that, it is going pretty slow. Great. Now in this statement, if you see, there is a word called, it is an interaction between charges. So charges are kind of a property. So when these people are doing experiments, they figured out there are at least two types. So far, at least we have seen only two types. Charges are of two types. We have classified them as positive charge and negative charge. This is completely arbitrary. Matlab, there is no reason why it has to be positive or negative. So an example of a positive charge is a proton. The charge is given symbol Q, which is plus 1.6 into 10 power minus 19 coulombs. That's your SI unit. And we take negative charge. Example, if you take an electron, the charge is given by minus 1.6 into 10 power minus 19 coulombs. Now be careful here. The sign simply indicates they're of different nature. The sign means nothing. And technically speaking, right, they should have defined electron as a positive charge. Because if you remember the definition of a current, how do we define current? The flow of positive charge is called current. But later on, these people realized, positive charge does not flow. What flows are actually electrons. So whenever you say current is flowing this way, in reality, electrons are going in the opposite direction. But unfortunately, by then we have already printed the books, so changing is very expensive and creates a lot of confusion. So we are just stuck to it. Yeah. So positive, negative, really they mean nothing other than there are two different types. You could have simply called it A and B. You could have even called it good and bad. It doesn't even matter. So the thing is simply there are two different types. Okay. So here the sign indicates. We got a bit of a theory today. They are of different nature. Don't think mechanics has left you. It will never leave you. It will always keep haunting you. So you can't say, plus 5 coulombs is greater than minus 5 coulombs. It doesn't make sense. This has no sense. Getting it? So there's nothing like positive charges are greater than negative charge. It's not a number. Getting it? The plus and minus is simply an indication they're of different nature. Clear with this? Any doubts on this page? Clear? So then we classified the charges are of two types. You can put down the main points. Don't worry about the notes. I'll send you the PDF. Then properties of charge. So in an isolated system, charge is conserved. So if you take a system which is not connected to anything else, the charge cannot be changed. So if you take a body here, let's say with 5 electrons and let's say 10 protons. So here the total charge is plus 10e minus 5e, which is plus 5e. That's your total charge. Now let's say some of these electrons combined with the protons, and let's say you have created 3 neutrons. And let's say we have 2 electrons and now we have 7 protons. Now if you see, the number of charged particles have changed, but the total charge still remains the same. Neutrons are neutral. The total charge is plus 5e. So the number of charged particles need not be constant. Clear? Next thing. Charge is quantized. What is the meaning of this word quantized? Where did you hear this first? In Rhombus, where did you hear this word quantized? You heard it in chemistry, if you remember. In the model, the Bohr's theory, right? Angular momentum is quantized. So any charge transfer. So the meaning of quantization is this. Anything that you give or take has to be a multiple of a certain minimum quantity. For example, think about this way. Right now, the smallest denomination you can have, right, is like 50 paise, right? So a 50 paise coin is the smallest denomination that we have right now. I think even that is not, we don't use it much. It is 1 rupee, but let's say 50 paise is the smallest denomination that you have. That means any amount of cash that I give you has to be a multiple of 50 paise, meaning I can give you 23 rupees 50 paise. I can give you 1237 rupees 50 paise. I can give you like this. I can't give you 19 rupees 18 paise. I can't give you 81 rupees 83 paise, isn't it? So all transfers or everything that I give you has to be a multiple of a certain fixed quantity. So any charge transfer is an integral multiple of an electronic charge. Right? So if you have a body there, and if you say I'm giving charge Q, you can be sure this value Q must be equal to N into E, where N is an integer, and E ka value is 1.6 into 10 power minus 19. But the thing about this, right, in the last 4 5 years, right, people have found out there are charges, they even found out a fractional charges like 1/3 of an electron, 2/3 of an electron. So there are quarks and, these things, mesons, which are particles inside the protons and neutrons. So we'll not get into that part. But yeah, so overall, as a macro level, the statement is still valid, but it is not like, you can't get a fraction of a charge. People have found there are particles with a fraction of a charge, but at least for our level, this is decent enough. Clear with this? Any doubt on this page? Next thing. Clear, na? Devansh, Abhinav, Ahana, Chainil, Parth, Surya. Clear? Next one. Like charges repel. Standard statement. And like charges attract. Free electrons are responsible for charge transfers. That is, when you say a body is positively charged, understand it doesn't mean it has excess electrons. That's what I'm saying. Protons will never move from the system. It doesn't mean it has excess protons. When you say you have a positive charge, it means someone has removed electrons from here. So there's a deficiency of electrons. So that is when it becomes a positive charged. So a negative charged body meaning there are excess of electrons. So everything is counted only in terms of electrons. Protons will never move in a system. The protons are fixed inside the nucleus. So a positive charged body doesn't mean it will have excess protons. Initially, if in a neutral body, protons and electrons are equal, you must have removed more electrons from the system. Yeah. The last thing, the charge is independent of velocity. So if you take a particle and move it really fast, mass actually gets messed up. If you look at mass, we have something called m naught by root over 1 minus v square by c square. This m naught is your rest mass. So basically the relativistic effect is the speed of light. So any body that is moving actually has a mass slightly greater than its rest mass. And when you actually get pretty close to the speed of light, the mass will go off to infinity if v is equal to c. So mass actually changes. But in case of a charge, we don't have this kind of problems. No matter how fast you go, the charge remains constant. So yeah. Similarly, there is also an issue with the length and also with the time, but we'll not get into that thing. So keep this in mind. Quantities, mass, length, time are not constant. They do depend on the frame ka velocity. Clear, everyone? There, these are the main properties there. Next thing. Any doubt so far? Parth, Ojas, Soham, clear? Roja, Pratik? Next thing. So how do you create a charge on a system? So there are three ways you can create a charge on a system. The first one is by friction. So by rubbing two bodies against each other, so if you take two materials and if you rub them against each other, there will be a transfer of electrons. If you have your bed sheet, which is more soft, or if you have a velvet cloth or something, you must have seen this, isn't it? When you actually drag it on your skin or something, sometimes you see small, small sparks. Sometimes it's some kind of, sound, like fat, 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 karke, some kind of a sound you must have heard. Or, ever went on a treadmill and you touched it and you got a shock? The thing is, the treadmill ka, that thing is whatever is there, that belt which is rubbing continuously, right? When you're continuously rubbing, it gets charged. So the whole treadmill actually gets charged. So when you get on a treadmill and you touch it, suddenly it discharges and you get a shock. After getting a shock, try to touch it again, nothing happens because you already discharged it. Right. So this thing you'll also notice, near where? Near escalators. Escalators, right? Because they're continuously moving, right? They're rubbing against it. If you touch any rod or something in a, the mall, sometimes you'll get a shock. Ever had a shock like that? Treadmill, though, you'll get it pretty normal. So this we also call as a static electricity. So these electrons are transferred between them. So if you take two identical bodies, let's say mass m, they're neutral, but they have a lot of electrons. And now let's say you rub them against each other. You will notice it is random. One body does become positive, one body becomes negative. So this guy becomes plus q and this guy becomes minus q. So when I say plus q, you actually lost electrons. Electrons must have gone from left to right. So this guy ka mass becomes m minus dm. So if you have two identical bodies, a positive charge will have a slightly less mass. Negligible, but yeah, theoretically the mass does change. Clear, everyone? This is actually a very, common thing. You'll actually notice this. If you ever seen an oil tanker, the tankers, which refill oil in the petrol bunks, or this, the tanks, this lorries which carry this gas cylinders, a lot of gas. Next time if you get a chance, try to observe them. So these lorries, right, they have, so here somewhere, right, there is a small rod. They have a rod there. So what happens is these lorries, right, when they go on a road, especially during summers, the tires are continuously rubbing against the floor, the road. Getting it? And because of that continuous rubbing, the whole lorry gets charged up. So when you're going there to deliver your petrol or gas or something, right? First thing what these people do, they take this rod and they put it on the ground. Then they open the fuel tank. If you don't do that, right, without doing this, if you just open the fuel tank and when the fuel comes out, the moment it touches whatever is the container, there'll be a difference in voltage. You can get a spark. So what these people do, they keep that rod on the floor first. So all the whatever charge accumulated will get discharged, right? And then you open it up. There is no criteria reduction. Meaning if both are identical materials, then it is random. But if the materials are different, then yeah, the material which is little more conducting will lose more electrons first. Getting it? This one. And this actually happened also. I think somewhere in 1920s or 30s. Ever anyone heard about this Hindenburg incident? So during 1920s and 30s, right, people were not using aeroplanes. They used to use something called zeppelins. You know, this big gas ka thing. You know, they used to have one propeller or something like this. So this is like a big gas thing, normally filled with hydrogen gas. So they used to travel on these things, you know, from New York to Europe. It used to take around 4 days of journey going over the Atlantic Ocean. Kind of safe actually, and yeah, you can fly. So one day, what happened while coming back from Europe? Right, there was a big thunderstorm. It passed through that. Now understand one thing: voltage is not the problem. You don't die because of high voltage. You die because of voltage difference. Getting it? So this thing passed through a thundercloud, and this whole thing became charged. So that was not a problem. Getting it? Meaning, think of like this. This happened actually a few years back in Vikhroli. The local train was going, and the override, the high tension cable snapped. That was a 10,000 volts of wire. It fell on the train, the local train, and the train stopped. Now imagine you're sitting in that kind of a train. A 10,000 cable falls on the train, and you're sitting there. What will you do? Option one: start shouting, jumping, and start kicking everyone. Right. Option two: you can just shut your mouth and sit there. Option three: aram se get down from the train. Right. Or option four: jump from the train. What do you guys think you should do? First option looks interesting. You can start shouting, crying, and you can do all nonsense. The best thing you can do is to just keep calm and just sit inside. The thing is, here the voltage is 10,000. Here the voltage is 10,000. So when you're sitting there, the potential difference is zero. It doesn't matter. You're actually safe, right? The second best thing to do is what? If at all you have to get down, jump in such a way, jump with both the legs outside at the same time. Don't touch the train when you're touching the ground. The worst thing you can do is getting down aram se with one hand here and one leg on the ground. That is the worst thing you can do. This will give you a 10,000 voltage and the ground is zero. You will get fried. Getting it normally whenever you get a shock, right? People think the current shock stops your heart. That's the secondary thing. The primary thing, right? You get a third-degree burns, and 10,000 volts is too much. That is the worst thing you can do. You should not be touching the ground and the train at the same time. So anyways, so this thing got whole charged up. So finally it came to the airport, and in order to tie it down, someone threw a rope. As this rope came down and touched the ground, there was a small spark, and it is a hydrogen gas. The whole thing busted. The whole thing burned down in less than like 10 minutes. I think most of the people in the passengers died. So this static electricity, right? This is not a joke. This thing actually has a lot of issues. Why all that? When astronauts were walking on moon, these people have found out the moon surface was very rough. You need to understand. When you're walking on the earth, you know what you're doing? You're actually walking on a cushion of air molecules. So there are air molecules between your feet and the ground. So every time you walk, you're stamping on the air molecules and you're going. So there's a cushioning effect. On moon, there is no atmosphere. So the surface is very rough. So when the astronauts are walking, the astronauts are getting charged up. And when they go and touch the space shuttle, the discharge, there was electricity passing through their suits, and all the sensitive equipment are getting messed up. So what they did then for the spacesuit, right? You have a small rod here like this. So when you're walking, that rod continuously touches the ground every time, and you discharge the electricity. So the static thing, right? Even though it looks theoretical, yeah, it does create a lot of problems for us. So that is one. So for friction, so that is one way you can create. I think a velvet cloth and a glass rod is a very good material. You get a lot of static electricity. In case if you can't get a velvet cloth, a cat is also good. Cat ka skin also has a property like. So if you take two cats and rub them against each other and leave them, one cat becomes positive, one cat becomes negative. They attract each other. Interesting thing, but yeah, I never tried it. But yeah, cat ka skin is similar to velvet. It works. Dogs, I'm not sure. So by conduction, so what happens here when you take two conductors? Are brought in contact. Charge transfers till potential becomes same. What is this potential and stuff? We'll be seeing that in the later part of the chapter. But again, if you take two identical bodies, let's say this thing has a charge of plus 3q, and if you have a charge of minus q. If the bodies are not identical, the distribution won't be symmetrical. So when you close the switch, this will get plus q and this will get plus q. They'll get equal and identical charges. The total charge is plus 2q. It will share equally between them. So whenever you touch conductors, charge can be transferred from one point to another. Clear with this? So that is the second way of reading a charge. One is friction by rubbing. Second is conduction by touching two conductors. The third one, any doubts on this page? Clear so far? The third one is by induction. So in induction, what you do when you take a charge, is placed in front of a body. It induces charge. So if you take any neutral body here and if you put a plus q in front of it, see what happens is when you keep a plus charge, now in this conductor or any body, you have a lot of free electrons. So the electrons inside will start getting attracted towards this plus q. And in this process, what will happen? All the electrons will come closer here. And because the electrons have gone here, you'll get a positive charge here. Again, understand, positive charge is not actually a charge, it's an absence of electron. So this guy becomes minus q and this guy becomes plus q. Because it is an overall neutral, the charge has to be still zero. So think of like this. Let's say if there is a concert or something going on here, what will happen? All the people will come towards the concert, right? In this process, all the seats at the back will become vacant. So something like that. When you keep a plus charge in front of this, the electrons get attracted to it. So you get more electrons closer. And the other side, the seats become vacant. So you get a positive charge here. So here electrons get attracted towards the plus q charge. And something interesting happens here. If you see the plus q and minus q are more closer, right? Then plus q and plus small q. So even though the charges are identical, the attraction force is more stronger than repulsion. Therefore, they attract. So this is one thing you should know. Even though we wrote the statement, unlike charges attract, you can even attract a neutral body. Think about this. School me must have done this now. You comb your hair and put it near the pieces of paper, and the papers get attracted. Ever done this? Now, look at that experiment, what you did. You took a comb and you combed your hair, right? So the comb became charged, your hair became charged. But when you kept near the paper, paper is still neutral, right? You didn't touch the paper, but paper still got attracted. So this is not conduction or friction. This is induction. When you put this comb near the paper, you started inducing charges on the paper and the paper got attracted. So rubbing the comb against your hair is friction. When you kept near the paper, you're inducing. Similarly, if you had kept negative charge, what would have happened? If you had kept negative charge, the electrons would have got repelled. So imagine if I bring a stick and start beating people, what will happen? People in the first bench will vacate, right? They won't try to sit in the front bench. Everyone will sit at the back. So seats in the front will become vacant. So we'll get negative charge here. So this will be plus Q and this will be minus Q. So here also you'll notice the attraction force is more stronger than repulsion. So it doesn't matter what charge you bring. You put a positive charge or a negative charge, they will attract. There. This is the third way you can create a charge on a system. Clear with this? Now, like I said, it is very difficult to show you a charge. So all we can see is we can see the phenomena, and from there we can try to figure out, oh, okay, this is happening because of the charge. That is how the science works. So let me show you something. Is the audio clear, everyone? Okay, now see. So we have few things there. You can see them, and then I'll ask you what happened. You try to explain it to me. So we have styrofoam plates. You must have seen this, right? These are the plates where you just eat. So these things can be tried at home. And we got a cloth. So this person has rubbed this thing, the styrofoam plate. Then they brought the styrofoam plate, kept it on top of it. It repelled. Can you see it's getting repelled? Look at that again. What happened? We took a styrofoam plate. We rubbed it. Then you took it, kept it on the other one. They got repelled. What's happening? What do you think happened? So first thing was clear, na? When you rubbed it, what did you do? By friction, you charged up the styrofoam plate. Then what happened? You brought the styrofoam plate and touched the other styrofoam plate. So when you're touching the another styrofoam plate, by conduction, the charge got transferred to the other styrofoam plate. Now both the styrofoam plates became like charged, isn't it? That is the reason they're getting repelled. You get the thing? So this is an example of case 1 and case 2. You're having both of them. Now see, styrofoam plate is this thing. So it became charged. Positive, negative, we don't know. Let's assume it became positive. Now see, when you're keeping it here, there is no repulsion. When you touched it, this thing is a little blur. When you touched it, now both the plates became like charged. This is conduction. Now see, when she removes the hand, now they repel. Clear? So there is friction and conduction. Simple experiment you can try at home. If you have a very small sibling, you can scare it. It is not really earth based. Styrofoam plates are not really that great conductors. The floor must be a plastic. Look at this thing. You rub the rod, you didn't touch the metal can. This is friction and induction. I'll post the video in the group. You can check it out more arams, but there. There you some liquid, milk or dosa there, then get a bubble. So this induction, right, happens even with soap bubbles also. Not only metal cans and conductors, you can do with even their soap bubbles. Yeah, they do wear plastic, right? You have to keep this on a plastic surface, an insulator. This is fine. You can check that out. They get repelled actually. Look at this thing. If you get this near the water, even the water bends. So this induction rate happens irrespective of the body. You can put it on a neutral body also, it will induce. This is an important one, electroscope. So this is the primary experiment, right, through which we figured out, okay, there is a charge. Just look at this. I'll explain you what is the experiment exactly. So we made these are some aluminum foils. So initially they're sticking to each other. So when you rubbed it, it became charged. See what is happening. As you get them closer, these two repel each other. Can you see how they're flying away from each other? So this is how we know there is something called charge. Getting it? No one actually goes and gets to see the charge. We have a cloth there. There. So they became like charge. So they're repelling each other. Look at this. So they made a lot of plastic threads kind of thing. They're like a jellyfish kind of thing. Now you are rubbing it. Now when you're rubbing it, the whole thing becomes positive or negative charge, but they all become like charged. When you take some, now see, they get repelled with each other. So you can see how they flew off. If you have an younger sibling, you should definitely do this and scare them out. Like you tell them, you don't listen to me. I know black magic and all that stuff. So yeah. And this is what happens, when you get a hit by a thunderbolt or when you get an electric shock. These are called Liechtenstein figures. Can you see how? So you actually get a free tattoo by nature. So when the electricity hits you, that's how it spreads over, how it is branching out and everything. So people who got hit by this thing, that's what you can see there. So that is there. Clear with that? So we can't see the charge, but you can see the phenomena due to the charge. So if we talk about that electroscope there, what exactly happened? So let's say this rod has become positive charged. So when you bring it close to this metal here, this will induce a negative charge by induction. If this is a negative charge, the other side becomes positive charged. So these aluminum foils become like charge and they repel. So this was actually what was happening in that. This is the reason why the two foils are repelling each other. And this experiment, right, is what we call as an electroscope. Getting the setup, how it works, right? So when you bring this charge near this metal conductor, that will induce a charge and you'll get an opposite charge on the other side. And because both are metals, they'll get like charged by conduction and they will repel each other. Clear, everyone? So that's a little bit of a theory there about the properties of charge and how can charge be created in a system. So having an idea is important about all this. Clear? Any doubt so far? Let's see one small easy question and then we will go ahead. Now all this stuff, right, you won't find this in gravitation, because gravitation where there's no concept of conduction, there's no concept of induction, right? So that way, if you see, electrostatics is a superior chapter. Now, if you have four identical bodies here, A, B, C, and D, right? It is given A is positively charged, and it is given A and B repel each other, B and C attract, B and D attract, C and D also attract. So this is what we have observed. Using this information, can you find the charges on BCD? I just want you to tell me whether it is positive or negative. You got an answer? Please type in the chat box here to the co-host. Hmm. Then how will B and D attract Abhinav? Ah, Purvaja. But is that the only answer? Hmm. So the thing is, like, we always keep remembering that only like charges, repel, and like charges attract. That's the problem there. We forgot something there. To attract, you did not have a charge. You can be neutral also. So there are two possible answers here. Now see, A is positive given. So B has to be positive because they repel. There's no option. Now you said B and C attract. Now there are two options. C could have been negative or C could have been neutral, right? Now you said B and D also attract. Now you can say this is negative, but there's a problem. If D is negative, then C and D will repel, right? So C and D both can't be negative. So that means D has to be neutral. Then this has to be negative. So there we have two answers. So C and D may one is neutral and one is negative. Which one we don't know, but C and D both are not charged. Is that clear, everyone? Simple one, mostly a CET level question or a easy one in mains level. So yeah, concept wise, you need to understand that way. You can't have C and D both charged. Clear with this? Easy one. Next thing. Any doubts on this? Kritik, Palak, clear? Kavya, got this? Next one. Coulomb's law. Primarily, we are going to play today only with this one equation, Coulomb's law. So what this thing says, the force between charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. So yeah, there's one more word, in vacuum. So if it is not vacuum, we will define it later on. We will talk about that in a bit. So if you have two charges, Q1 and Q2, and if the distance between them is R, so they will repel each other. So this thing will be F21. So the meaning of this is force on 2 charge 2 due to 1. Similarly, this thing force will be F12. This is the force on 1 due to charge 2. And by Newton's third law, the force on 1, 2 will be opposite of force on 2, 1. Equal and opposite. If you repel me with certain force, I will repel you with the same force. Right? And the magnitude of this is given by F is equal to 1 by 4 pi epsilon. It's a constant Q1, Q2 by R square. For simplicity, we write this thing as K, Q1, Q2 by R square, so that this thing kind of looks like gravitation. If anyone has done gravitation in school, you must have realized gravitation का formula क्या था? G m1 m2 by R square. You can see the resemblance. In place of mass, you have charge Q. In place of G, we have K. Mathematically, they look identical. So this value of K, which is 1 by 4 pi epsilon, is given by 9 into 10 power 9. This epsilon is called electric permittivity. We will discuss about this later on. Permittivity of vacuum, whose value is given by 8.85 into 10 power minus 12. There, you can note down this thing in the red box. We will need that formula there. And remember, whatever we derived here, these formulas here, these are valid only for point charges. If the body has a certain size and shape, you can't use these formulas. There, one simple formula I gave. If there are two charges, force between them is K, Q1, Q2 by R squared. That's it. That is the one thing we're going to play with around today. We have some pretty good ones on that, but you can note it down. Clear, everyone? Now, if you look at the vector form, now if you look at the vector form, so if you have charge Q1, charge Q2, so this force on this will be F21. So this can be written as F21 will be K, Q1, Q2 by R square, and the vector will go from 1 to 2. So we are looking at a vector which is going from 1 to 2. This is your vector R12 bar. Right? So here the positive force indicates repulsion. Remember, positive force, negative force doesn't mean one is bigger and one is smaller. If you get a negative force, it means attraction. So you can actually, while drawing the FBD, you can draw the direction and you can use the formula only for magnitude. Positive force indicates repulsion. And if you have multiple charges, let's say if you have Q1, Q2, so on till Qn. So let's say this guy is giving force F1 bar, this guy is giving force F2 bar, this guy is giving force Fn bar. Just like vectors, the net force on the charge Q can be simply the vector sum of all forces, meaning I cap, J cap, you can resolve them and add them up. There. So all your vectors and Newton's laws of motion, everything is valid. The only thing that F ka value is given by K, Q1, Q2 by R square. Is this clear, everyone? Adi, Arush, clear with this? Agasya, clear with this? Devansh, Daksha, Vihan, Niharika, clear? Any doubt so far? Ishana, got this? Clear, na, Janil? Turn in the page. Let's see a question. Let's see a question. So we have three charges here. Let's say this is A, whose coordinates are 2, 3, 1. We have another point B, which is like 4, 1, 3. And let's say we have another point here, which is -2, -3, -2. So at point A, we have charge plus Q, and let's say here we have charge -2Q, and let's say here we have charge 3Q. So three different charges in three-dimensional plane. So find the force on charge A due to B and C. This should be a mains level question. So this B here will attract, this C here will repel. I want to the resultant of the forces, IJ cap. Let's get this. Let's give it a try. I'll give you 2-3 minutes. And remember, I only taught you one formula till now. The force is K, Q1, Q2 by R square. That's it. Anyone confused with the question? The diagram is not clear. Anything you're not convinced here, please ask. How did you get that, Arush? You didn't even get any I cap, J cap, K cap. So according to your logic, if you get I plus J cap, you can write it as 2. Vectors, everyone, you can't just add I cap and J cap there. Let's see. Now look at this. If I look at the force between A and B, K, the charges will be Q minus 2Q. I'll just keep them, assume they're positive charges. The signs will take care of it. By the distance between them will be AB ka square, mod AB ka square. And this will be how much? BA bar. Now you can clearly see the thing here. BA cap. So that is one way to do. Or if you want, you can, the minus n will come out automatically. So what is BA bar? Right. So that is one way, or you can do like this also. Since I know it is negative, it will attract. This will be force between AB. Since I know they will repel each other, this will be force CA. So then I can just ignore the signs and take the magnitude. So either way, it works. So you see which is convenient for you, whichever is you're more comfortable, right? If you want, you can just take it in the normal. You can assume B and C are positive, and you can get the equation like this. So we have BA bar. This is FCA. So BA bar, you know how to find vector. So B to A is final and B is initial. So 2 minus 4 minus 2I cap, 3 minus 1, 2J cap, and 1 minus 3 and 2K cap. So from here, we'll get the magnitude of mod BA bar, which is root over 2 square, 2 square, 2 square, 4 root 12, and that's 2 root 3. So from here, you can get a unit vector BA cap, which is the vector by its own magnitude. That y will be minus I plus j minus k by root 3. There. I know everything here. So this guy will be minus k q square. 2k q square by AB bar is 2 root 3 whole square into BA cap. So you can clearly see the force is actually from A to B. So minus of BA cap will be AB cap. So the signs take care of it. Similarly, when you go from C to A, or like I said, if that vector thing is getting confusing, forget about the sign here. Just treat it as plus, take the magnitude of this and write the vector AB cap. Is that making sense? You can do it either way. Draw the FBD and get the vector, or try to get in a vector form, whichever you're comfortable. So this is FCA will be KQ 3Q by CA bar ka square, and this will be CA cap. So CA bar will be how much? You're going from C to A, so A is final. So 2 minus 2, that is 4I cap. 3 minus, that is 6J cap. 1 minus 2 plus 3K cap. So the magnitude of CA bar will be root over, how much is that? 36, 9, 45, 16, 45, 16, root 61. Numbers are bad. So again, we know CA cap will be CA bar by mod CA. So this guy will be 3KQ square by 61 and CA cap. There, you're done. So the net force on charge A, you can just add these two vectors, force AB plus force CA. That will give the final answer. Is that clear, everyone? So it's all about vectors. So K, Q1, Q2 by R square. R is the distance between them. That thing you could have got even from the distance formula. Or you could have got the vectors and from there you could have got it. Either way, it would have worked out. Check this out. There, all we did is just vectors. I didn't teach you anything new there. The only thing, the formula was K, Q1, Q2 by R square. Is this clear, everyone? Clear, Nikhil? Jainil? Taksha? Purva? Clear with this? Niharika? Ishana? Ahana? Clear? Let's see one more. Because why do you take FC? And because C and D are repelling na regard. Force is from C to A vector, isn't it? The force is going from C to A. C is repelling A, so it will go away from C. B is attracting A, so the vector will come towards B. Sure? That way. So this minus BA cap will become AB cap. So yeah, you can do that. Next one. We got a clock. At the center, we have a charge minus Q. And here we have 12Q, 1Q, 2Q, 3Q. Just like a clock, 4Q. But this is, they're not exactly up to the thing, but yeah, they're equally spaced, just like a clock, 7Q, 8Q, 9Q. There. So there are 12 charges on a circle, and we have a minus q charge at the center. And the radius of this circle is r. Find the net force on minus q. So charges are placed on a clock. So the angle between two consecutive charges is 30 degrees. Let's get this. No, that's not vertically upwards. So if I have to ask you a simpler question of this, can you tell me the direction of the force? Let's start from there. Options will be like this: towards 9q, towards 10q, towards 11q, towards 8q, towards 3, towards 2, between 10 and 11, between 9 and 10, between 9 and 8, between 2 and 3, between 3 and 4. ऐसा options होगा. नहीं Rahana, that's not the answer. Jainil, you are right. Purvaja, that is wrong. Remember, every charge is not giving an equal force. No, Abhinav, that is not right. I don't know what you even typed exactly. Where is k, q, and q to my r square? But where are the pairs, God? So what is the answer, Vihan? Tell me that, na. Think, I'll give you another minute, then I'll show you. Nere Devansh, you were such a good answer. That one way to do is a brute force. You can literally take each force and then divide I cap, J cap, and then add them up. No, Kritik, that is wrong. The direction is between 9 and 10. There. I'll show you how, but yeah, that is an answer. That's a direction. Think. Another 30, 40 seconds, and then I'll show you. Let's see. So what I would suggest, instead of directly going brute force and trying to solve for each force, there is a much better way. You should always try to use, make use of symmetries. So this distribution which I have, I will try to split this. Look at this. So what I will do, right? I will write this 12q as 6q and 6q. I'll split it into two charges. I will write 11q as 6q and 5q. I'll write 10q as 6q and 4q. 6q and 3q. 6q and 2q. 6q and q. Now see what happens. Now if you look at the pairs here, this q here and this q here will cancel. This 6q and this 6q will cancel. This 2q will cancel. This 3 will cancel. 4 and 4 will cancel, and 5 and 5 will cancel. Can you see that? So oppositely, you can just cancel off the charges because the exact equal and opposite forces. Now this diagram becomes like this. So here we have 6q, we have 6q, we have 6q. Can you see? Now there's a symmetry there. Now we have 6q, now we have 6q, and now we have 6q. The whole question becomes as if there are 6 charges of 6q. This looks more symmetrical, isn't it? Be careful, there's no charge on 6 o'clock. That is gone. So you have charges from 7 o'clock to 12 o'clock. Is this making sense? 1 to 6 will get cancelled. So 7, 8, 9, 10, 11, 12, these will be remaining there. Now it is more easy to figure out. So here we have a minus q charge. Now look at the symmetry there. So this 6q will attract up. So let the force be F. And I know the value of force F. So F is nothing but K 6q small q by r square. I'm ignoring the minus sign. It means attraction. So that is force F and this is force F. You can see by symmetry, this resultant will be through the middle. What is this angle? 75 and 75. Agreed? Between two numbers, you have 30 degrees. So 30, 60, 90, 120, 150. And because the forces are equal in magnitude, the resultant will be a bisector. Is that clear, everyone? Then, if you look at these two guys, so this guy will attract this way with F, and this will attract this way with F. And this angle between them is 30, 60, 90, 45, 45. So this angle is 45 and this angle is 45. This resultant is also along the bisector. You're getting what I'm doing? By taking two charges, I can get a pair and they will be the bisector. And for all of them, the bisector is the same. Then if I take this guy, this is also F and this is also F. This angle will be 15 degrees. You're done. So therefore, the force on the charge minus Q will be 2F cos 75 plus 2F cos 45 plus 2F cos 15. And the direction will be between 9 and 10. That's the magnitude and that's the direction. Is this making sense, Ario? Quite a useful technique, right? If I give you some charges like that, you can always cancel off like this. Instead of finding due to each one and adding up, this is much faster. You got the angle, I got. This is 15 degrees. That much you can resolve, right? Now, get a unit vector in that direction. Cos 15 I cap minus cos 15 I cap plus sine 15 j cap. There, you got a unit vector. Put it there. You're done. You want that? I can write it down. The direction will be minus cos 15 I cap minus sine 15 j cap. There, that's your unit vector. Basically, it is between 9 and 10. Clear with this? No, they can ask you things like this also. For example, if I give you something like this, let's say we have an hexagon here, and let's say this is plus q, minus 2q, 3q, minus 4q, plus 5q, and minus 6q. If I give something like this, how do we solve this? Same thing. Let's say we have a charge q in the center. Every time you might not get a very beautiful pair, but how do we do this? Find the force on small q, roughly. Think I'll give you a minute. What I can do, I can add 3q, I can add minus 3q, I can add 5q, I can add minus 5q, right? I can add plus q and minus q. So this 3q goes off, this q goes off, this 5q and 5q goes off. So you will get a new thing where this guy will become minus 9q, this guy will become minus 7q, and this guy will become minus 5q. You can clearly see here, so this guy will apply 7f force, this guy will apply 9f force, and this guy will apply 5f force. And all the angles between are 120 degrees. So this is 60 and this is 60. So this resultant will be 9f minus 7f plus 5f cos 60 minus I cap. And the vertical direction, you'll have 7f minus 5f sine 60 j cap. Easy. So you will get three vectors like equilateral triangle, but they're not of equal magnitude. So 9, 7, and 5. You could have done it any other way also. The answer won't matter. It will come the same. Clear with this? Instead of trying to find the force due to all the six, you can eliminate three forces. So saves you a little bit of time. Clear with this technique, everyone? There is another way of doing this. Like I said, there are multiple ways to do this. Plus q. This is 3q, right? I can write this as plus q and 2q. This is 5q now. I can write this as plus q and 4q. Now this plus q, this plus q, this plus q will cancel now because they form an equilateral triangle. Now you can even cancel 3 pairs. You're getting it? But then you'll get 4 charges remaining. So it works. You can cancel it however you want. It doesn't matter. It works. Any doubts on this? And if you can see the whole question, it is more of a vectors. Once you wrote k q by r square, electrostatics got over here. Next one. We have an incline, angle theta, friction is mu. Mu is less than tan theta, so less than angle of repose. So if you keep a block here, it is going to slide. And let's say block ka charge is plus q. Here we have a charge plus q here fixed. So this plus q and the charge plus q are repelling each other, and this is the distance between them. So you kept a block on a rough surface and you kept another plus q charge at the ground level to repel it and keep it in equilibrium. So find the value of x if the system is in equilibrium. Friction, everyone. Told you, your mechanics will keep haunting you. Let's get this. What is the distance between the block and the charge so that the system remains at rest? Both have identical charge plus Q. So let me ask you this. How many answers are there? Let's start with that question. How many answers are there? There are infinite answers. Now try. And you have seen a similar problem. Not based on repulsion. Two, there are infinite answers, God. X can take any value. That doesn't make sense. So I'll put X at infinity. Then just because it's infinite answers doesn't mean any value. What are those defined values, Ravi, now? एग्जाम में ये लिख के हो गया क्या? What's happening here? Right, Poroja, but or नहीं होगा. It is something else. See what is happening here. You guys are forgetting something. Is friction ka job is to apply maximum force. So let me give you a hint. Let's say I have a block on a floor. Let's say 10 kg. Listen everyone clearly. And let's say mu is equal to 0.2. What is the maximum friction? Mu into n. So that is 0.2 into 100, which is 20 Newton. So this is the maximum friction. Now you tell me, if I apply F is equal to 5 Newton, what is the friction? Will it be 20? Just imagine if this was 20, what would have happened? The block would have gone back, right? I mean, just think about it. I'm pushing forward and it is going backward. Doesn't make sense. So what will be the friction then? Friction also will be 5. Suppose if I apply F is equal to 10, then what will be the friction? 10. If I apply F is equal to 15, then what is the friction? 15. If F is 21, then what will happen? Then friction will be 20, isn't it? Friction will give only how much ever is required. Friction will not give maximum. So here you're dealing with a force which is self-adjustable and which can also change its direction. So the first case, let's say you bring it very close to it, the minimum distance. You bring this charge, the block so close, the repulsion is very strong. What would happen? The block will try to go up. So if you push the block very close to the charge, it tries to push up. So if it tries to go up, then the forces will be this way. The repulsion force will be kq square by x square. I'll just write it as F. We have mg sine theta acting downward. And then we also have friction acting downward. So friction will be downward. So from here we get the force kq square by x minimum square. So you have a maximum repulsion is equal to mg sine theta plus mu mg cos theta. This gives you the minimum distance. The other case, you keep the block so far, this distance will be maximum distance. So you kept the block so far, the repulsion is very weak. The block will try to come down. Then the repulsion will be upward. Friction also will be upward. You're getting it? This is the problem with the friction, and that's why we had a separate chapter for it. Friction can change its direction and can change its magnitude. So this will give you kq square by x max square will be mg sine theta minus mu mg cos theta. So your answer will lie between the maximum and minimum. You can take any value between them and the friction will adjust the value for you. And you know where you have seen this problem? We have seen this in friction. I'll write it down. You can refer this later on. This problem, if you remember, we had a block on an incline and we had another block is hanging on the other side. And the question was find the mass m so that this 10 root 2 kg block is at rest. And then if you see here also we had cases. If the block m is too light, then what will happen? The block will try to slide down. If the block m is very heavy, then this thing will try to come up. So you get an answer between 5 and 15 kg. Friction did not take always the maximum value. It could have taken anything. Are you getting this? Then see, we even wrote this thing also. See, for different values of tension, we had different values of friction. So friction ka value was adjusting its direction and adjusting its magnitude. Now, did you guys remember this question? So there, that's an important one there. So I'll write it down. You can refer page 42, friction notes. So this problem is actually based on that. Instead of taking another block, I have just taken a repulsion due to the charge and we wrapped it up. Clear with this? All clear with this? Any doubts on this? Take a break. Come back by 7:05. We'll continue from here. Any doubts so far? Okay, take a break. Come back in 10 minutes if you have no doubts. Yeah, let's start off. So we have two pendulums. Let's say this is Q2, mass is M. This is Q1 and mass is M. Same masses. Gravity is there. Length of the strings are L. So with the vertical, let's say this is making an angle alpha, and let's say this is making an angle beta. Find alpha and beta in equilibrium. So these two pendulums are repelling each other, and in steady state, they form angles alpha and beta with the vertical. Find the angles alpha and beta in steady state. This is a standard question. We'll see something better next. So let me ask you a simpler question. Which is bigger, alpha or beta? Start from there. Which is bigger, alpha or beta? Right, Surya. What about others? Yeah. The general misconception, na, people think like this. So if I give you like this, let's say Q1 is greater than Q2, then can you tell me which is greater? It doesn't matter. They're equal. Why? What is the force between them? K, Q1, Q2 by R square, isn't it? It's a product now. And by Newton's third law, they'll have equal and opposite forces. Just because one charge is bigger than the other, for example, see, if I take a charge of 1000 Q and if I take a charge of 0.1 Q, so if I ask you what is the force between them, you think the forces will be different? The force is same. It depends on the product of the charges. It doesn't depend how big the charge is or how small the charge is. So forces are equal. Weight is equal. Everything is equal. Then alpha must be equal to beta, isn't it? If repulsion force is equal, mg is equal, length is equal, then yeah, alpha has to be equal to beta. Symmetry. Then you're done. Then it's an easy one from there. So this is how it looks. Draw the FBD of this thing, you will see. So if this is alpha and this is beta, if you look at the repulsion force, this will be tension. This will be KQ1, Q2 by R square. This will be mg. This angle will be alpha. Similarly, this repulsion will be KQ1 2 by R square. This will be mg. This will be beta. R is this distance between them. This would be L sine beta. And this will be L sine alpha. You can clearly see here by symmetry, tan alpha will be K Q1 Q2 by R square mg. This is also equal to tan beta. So we have tan alpha will be K Q1 Q2 by mg. R will be nothing but 2L sine alpha ka square. You can shift it that side. You'll get tan alpha sine square alpha. There you can leave the answer here. This K Q1 Q2 by 4L square mg. That's your answer, everyone. So when do angles get affected? The angles don't get affected by charges, they get affected due to masses. So that is a thing you can keep in mind. So angles change. So if you mess up the masses M1 and M2, then you'll get different angles. The angles depend on the mass and length of the strings. Same thing, if you don't keep the equal lengths of the string, they won't be horizontal. They will get messed up. Clear, everyone? Let's see a better one than this. This will be a mains level question. Any doubts on this? And remember, till now I'm teaching the same thing, KQ and Q2 by R square. I didn't teach you anything new. Next one. Suppose instead of one pendulum, you have three pendulums. All are length L. So three charged pendulums. So all have same charge plus Q and mass M. Now if you bring them closer, what will happen? They will repel each other. So they repel each other and they formed a shape like this. A tetrahedron. So they repelled each other and they formed a tetrahedron. What's a tetrahedron? All faces are equilateral triangles. So there are four faces. All faces are equilateral. Meaning if I have to show you, this is how it would look. There you can look at this picture here. So this was the point of suspension. So you have one charge here. You have one charge here. You have one charge here. Able to visualize how it is? So in this process, we have tension in the strings. So if they're repelling each other, there'll be a tension. Gravity is anyway there. So the question is, find tension in the string and find the value of charge q. So q ka value is not given. Only m is given, length is given. Find tension and charge on the pendulums. Find tension in the string. So it has to be given. It's a tetrahedron. If they don't give you, that shape could have been anything. There is no guarantee that the base will be an equilateral triangle. Find tension in the strings and charge q. The q ka value is not given. We need to find that also. Let's get this. I can extend this problem more. I can put n charges. Then we'll get an n-sided polygon at the bottom. The game is similar, but yeah, I think this should give you an idea. Let's try. Anyone didn't get the diagram, not convinced what is happening, please ask me. Question should be clear. Yeah, it's an equal triangle. I said no, all faces are equilateral. So how do we start? Start with the free body diagram of any one charge. mg by root 3. Okay. Interesting. How did you get the angles? I think that is wrong, Renickel. Ojas, any answers? Yeah, let's focus everyone. Focus on the class. Kritik? Yeah. You're there, na? Meaning you got mixed up in the background. All we can see is football. Yeah. Nikhil, check your angles now. Tension 2 आया क्या वहां ना? Isn't it root over 2 by 3? Let's see the diagram say. Let's look at this picture here. So this was the point of suspension. So if you look at this guy, this was the plus Q charge. Now, if you look at the forces here, we have tension here. We also have another charge here, plus Q. We have this charge, plus Q. So these forces are repelling this guy. So this will be like this, F, and this guy will be like this. This is F. Making sense? Also, you'll have mg. There are total 4 forces on each pendulum. Is the FBD clear, everyone? We have one tension, one mg, and there are 2 repulsions. Now from here, if you drop a perpendicular, this will come and meet at the centroid. Now from here, you can clearly see the symmetry here. This angles will be 30 degrees and this angle will be 30 degrees each. The problem we are facing is I need to get this angle here, theta. If I can get that angle, then the vertical component will be t sine theta and the horizontal component will be t cos theta. My problem will be solved. Then I can clearly say t sine theta is equal to mg. So I'll get tension is mg by sine theta. There I'll get it in one step if I know theta. And in the horizontal direction, t cos theta is balancing the 2 forces whose resultant is 2f cos 30. So t will be mg by sine theta. So this will become mg cot theta. This is 2. F will be k q square by l square because it's an equilateral triangle. All sides are l into cos 30. Now from here I can solve and I can get q ka value. Now the question is how to get that theta. So you're getting which theta I want? I want the angle made by this line with the horizontal surface. We are talking about this theta here. Hope everyone is getting which theta we are talking about. More of a geometry. So if you see the picture, you will realize you can actually get that easily. It's not that difficult. So if you look at this picture again, this was the point of suspension. This length is L. When you drop the perpendicular, this was the centroid. This angle was theta. And we know the centroid will divide the height in what ratio? 2:1. The base is an equilateral triangle, isn't it? The centroid will divide in the ratio of 2:1. So this guy from here to here will be 2/3 of the height, where height of a triangle is nothing but √3 a by 2. So this guy will be L by √3, isn't it? This will be 2 by 3 into √3 L by 2. That guy will be L by √3. There you're done. So what is cos theta? Cos theta is 1 by √3 adjacent by hypotenuse. Sin theta will be root over 1 minus cos square theta, which is root over 1 minus 1 by 3, that is root over 2 by 3. Are the angles clear, everyone? So once you draw the FBD, right, it is done. It's mostly about getting the angles. Is this making sense, everyone? Check out the steps. Ask me if you're confused with the free body diagram. How did I divide the components? How did I get the angles? The only thing about electrostatics in this thing is that F is kq square by L square. That's it. This is the only electrostatics part. Remaining everything else is NLM. And if you remember in NLM, we did more deadly ones than this. I think we did that in vectors, I guess. Where is that guy? This one. Anyone remember this problem? We had a particle hanging in the center of a cube and we had 3 strings. One is connected to B, C, and A. So this is the first time, where we divided angles in 3D. So something of this sort. So this was a much better one than that, but yeah. This was a question. We had a mass M hanging at the center of a cube, and then we had string here and string here and string here. 3 joints. The question was find the tension in the strings. This we did in basic maths and vectors. Is this question clear, everyone? Clear, Surya? Ahana, got the angle, no? Yeah. Next one. Let's see a little higher. Let's say we have a hexagon. We have charges on the vertices, plus q, plus q. We got 6 charges there. And then what you did from the center, at a particular height, you kept a charge minus q and mass m. So this is your center, y is equal to 0. So this charge is out of the plane, huh? And this height is y. You're getting how is the picture here? Meaning, if you're looking into my screen, this is how it would looks. If this is your hexagon, this guy is coming out like this. You're getting it? It is pointing out of the plane. The minus q charge is not in the plane, it is out of the plane like this. Like a tent. Able to visualize? The center one comes up. So now this 6 charges, what will they do? They will attract, right? So this will attract, 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 this will attract. So all 6 of them are attracting it down. So this is a regular hexagon of side L. So minus q charge of mass m is placed at a distance y above the center of a regular hexagon. So the first question, find force as function of y and plot the graph. Meaning I would have asked you the graph only directly, same thing actually. So plot f versus y graph. Find y for maximum force. So there's a particular value of y where you get a maximum force. Third, if y is very small, if y is much less than L, find time period for small oscillations. There, your SHM is back. So if you leave that minus q, it is just going to bounce up and down like this. So there is a time period there. Find the time period for small oscillations. This would be an advanced more than one choice question. If I ask you only the graph, that is also a decent question actually. Let's get this, everyone. Yeah, Rejanil, that is wrong. What did you do, Rejanil? When you're at the center, what will happen? All forces are equal. It will be 0. How is that maximum, God? That is not maximum. You'll get 0. When you're at center, force is 0. When you're at infinity, force is 0. That means somewhere in the middle, the force has increased and then decreased. You could have guessed the graph at least that much. No, Ojas, that is wrong. Try. Get the first 2 parts. And more of a max question again. I'll give you 2-3 minutes. Get the first 2 parts. kq square. Naresh, Anna. That is only due to one charge, isn't it? We forgot there are 6 charges. Surya, getting this? Try. Yeah. You also forgot 6 Revihan. Right, Poroja. So look at this. So if I take any one of them, let's say if I take this guy, right, the force F will be this direction. Let this angle be theta. And now in a regular hexagon, all sides are equal, even the distance from the center is equal. So this is L. So this is Y, this is R, this is L, and this is theta. R is nothing but root over L square plus Y square. Cos theta is nothing but Y by R. Perfect. Now you can clearly see here, if you look at this charge, how will the forces be? You can divide the force into components. You will get F cos theta, 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 F cos theta, and F cos theta. Like this, you get 6 hexagons, isn't it? In the horizontal plane, you will get 6 F cos theta, sorry, F sin thetas in the plane. So each force can be resolved into 2 components. F sin theta and F cos theta. And you'll have 6 F cos thetas acting downward. By symmetry, you can clearly see all F sin thetas cancel out. So what is the value of F? So F will be K. Remember, I'm only taking the magnitude. The direction is already taken care of. K Q by R square. So that will be K Q by L square plus Y square. Right, Puroja. Ishana, got that. Get the time period also. So there. So the force on this charge F net will be 6F cos theta. Substitute here 6. F will be K Q by L square plus Y square, and cos theta is nothing but Y by again root over L square plus Y square. Therefore, we get force is equal to 6 KQQ Y by L square plus Y square whole power 3 by 2. The direction minus J cap downward. This is your force. Right, Falak. Furuja mass आएगा ना उसमें. Forgot mass. Now you're asking find the maximum value of this force. What to do? Maximum, minimum. Differentiation, everyone. The first differential must be equal to 0. So this is a force which is depending as a function of y. Any doubts on this page, please ask me. So if you want to maximize this function, the first differential df by dy must be equal to 0. Any doubts on this page? Purva, clear with this thing? Kavya, clear? Agastya, got this? Then maximum minima differentiation, brute force. So you're differentiating dy by y, and this will be y by L square plus Y square whole power 3 by 2. I hope this much differentiation you can handle. So I'll use the product rule. So that will be dy by y is 1 by L square plus Y square whole power 3 by 2 plus y into minus 3 by 2 L square plus Y square whole power 5 by 2. Remember chain rule, we have to differentiate whatever is inside. That will be again another 2y equal to 0. you'll get 1 minus 3y square by L square plus y square is equal to 0. You get y is equal to plus or minus L by root 2. So there are 2 points you get a maximum force here. Now if you try to plot this graph, remember this, when y is positive, force is negative. When y is negative, force is upward. So the graph would look like this. At the center, force is 0. It would go negative maximum and then drops to infinity. It goes to positive maximum. This is how the graph looks, everyone. Symmetrical, but yeah, up and down. So when you're on the negative y-axis, that is when you're down, the force is up. When you're up, the force is down. There. So we have force is equal to 6k cube q y by L square plus y square whole power 3 by 2 is equal to minus mass into acceleration. If L is much, much greater than y, then you can write L square plus y square is approximately L square. You can ignore that. This guy suddenly becomes 6k q y by denominator becomes L cube into a. This looks like SHM. This is your omega square cut down. Therefore, the time period will be 2 pi root over ml cube by 6k cube. Check. Like I said, the SHM will just come in the end and hijack the whole problem. You just need to write F is equal to ma and get A in terms of omega square. That is the whole point of small oscillations. The denominator, you can make it, you can ignore the y in the denominator. If y is big, it becomes oscillatory motion. You can't find the time period. Is this clear, everyone? That is how you can frame a problem. You can bring SHM, you can bring the forces and everything. Look at this. Ask me if you have any doubt on this. Anyone not convinced with any part of it? The FBD, the forces, the maximum minima, or the time period. This is how the problems will be. So we will see as we go on. The problems will mix up a lot of mechanics. Even though we say electrostatics, the whole thing is like that. Clear, na, Niharika? Got this? Any doubts? Anyone not convinced with anything, please ask. Clear, na, Surya? Ojas? Soham? Sharman? Clear with this? Next one. Let's see a standard question. This is a PYQ. We have 3 charges, 4Q, we have plus Q, and you kept a charge Q at the center. Not the center, somewhere. This distance is X. This distance is D. All charges are free to move. Matlab nothing is fixed. So if you leave it like this, the 4Q and small capital Q will repel each other and they'll fly off. You don't want that to happen. So the question is, find X and find the value of small q so that system is in equilibrium. So where should I bring this charge small q and where should I keep it and what should be the value of the charge so that system remains in equilibrium? And just to give an idea, 4q and plus q will repel. So I can roughly guess q has to be negative. It should attract both of them inwards so that they don't fly away. So the whole system is in equilibrium. 4q is in equilibrium, q is in equilibrium, capital Q is in equilibrium. Let's get this. It's a standard model. And remember, whenever it's a standard model, these are the questions which will repeat in mains and bits. Right? Last 5 years, when you observe the papers, right, there's a lot of repetition. Maybe not the exact thing. They might change the numbers to 16q, but models will remain same. Yeah, let's get this. This is a standard one. You must have seen this before. But find the value of x and a small q. There are 2 things. Right, Falak. Right, Ishana. Got the distance. Get the charge. Right, Arya. Let's get the value of the charge. No, x is not 4d by 5, x is 2d by 3. Puruja, got the charge, get a sign also. Don't forget, because charges may you'll have two answers, positive and negative. You have to mark with the sign. Right, Surya, got the distance. Distance is 2d by 3, everyone. Look at this. So we have three things here. So I will draw FBD of small q. So if you draw FBD of small q, now again see, plus q ka charge I don't know, small q. So I'll assume it is positive. Let the signs take care of it. So this 4q is pushing to the right, which is k 4q small q by x square. This guy is also pushing because I'm assuming it is positive, k q by d minus x whole square. So this will be the distances. Since it is an equilibrium, both should be equal. So k 4q by x square is k q by d minus x whole square. Kq goes off, you'll get 4 is equal to x by d minus x whole square. This will be x is equal to 2d by 3. Similarly, if you try to draw FBD of 4q, remember that is also an equilibrium. You could have drawn for q also. This is 4q. Again, remember, I'm assuming small q is positive. I don't know the sign. So this guy will also push, which is k 4q small q by x square. This guy will also push, which is k q 4q by d square. I know that is not possible, so science will take care of it. Something is negative here. So k 4q by x square plus 4kq square by d square is equal to 0. We get q is equal to minus q x square by d square. X is 2d by 3, so minus 4q by 9. So there, you assume plus q as positive and let the sign take care of it. You don't worry about it, the sign will come automatically. Is that clear, everyone? So the small q has to be negative charge so that the 4q and plus q don't fly away from each other. That is a distance and that is a charge. Have a look at this. Clear, everyone? Any doubts on this? Clear? Simple equilibrium problem. Next thing. What happens if you put charges in a medium? So till now, if you see, whatever we did, everything was in vacuum. So if you have force on charges in a medium, something happens when you put the charges in a medium, things start getting messed up. The force, the Coulomb's law says, the force is Q1, Q2 by 4 pi epsilon medium r square. So that doesn't become epsilon naught anymore, it becomes epsilon m. We'll talk about that. So epsilon medium is nothing but epsilon relative into epsilon naught. So this epsilon r is nothing but just like relative density. It's called relative permittivity. But what does this mean exactly? Think about it. Where is epsilon in the equation? Epsilon is in the denominator, right? So if epsilon increases, will the force increase or decrease? Force decreases. That means this epsilon is kind of behaving like, a resistance, isn't it? So we can say like this. Higher the epsilon r, more difficult for charges to interact. Higher the epsilon, the more difficult for charges to interact. Not the right choice of words, but yeah, you can say something like it's kind of like a resistance. It somehow decreases the force. So this is similar to resistance. So something happens with the medium. So what Coulomb's law gives you, right? Actually, this F is not the force on the charge. This is the net force on each charge. So this F net force on each charge. Look at the choice of words I'm using. When I defined here, na, I said force between charges. This is the force between charges. Now suddenly I'm using something else here. It's a net force on each charge. We will talk about that. Is given by Q1, Q2 by 4 pi epsilon medium r square. So this can be written as Q1, Q2 by epsilon r 4 pi epsilon naught r square. That is nothing but force in vacuum by epsilon r. So force actually decreases. So if you put the charges in a medium, the net force on a charge becomes the force on a charge in vacuum by epsilon r. So by putting charges in a medium, the force on each of them decreases. Now the question is why? Now this is an experimental thing, great, but what is the reason? Why should the force decrease because you have a medium? Let's discuss about that in the next page. So this epsilon naught we defined is only for vacuums. And so this value rate epsilon r is always greater than equal to 1. And for vacuum it is. For vacuum epsilon r becomes equal to 1. There is one more name for this. This is also called as dielectric constant, relative permittivity or dielectric constant. So same thing, but yeah, we have two different words for this. Is this clear, everyone? So force decreases. Let's see why the force decreases now. So this thing you should know. Why does the force decrease? Now say, if I take two charges, Q1 and Q2, we studied today, if you're going to put a medium or if you're going to put a body in front of a charge, what happens? If you put a body in front of a charge, what happens? You induce charge, isn't it? So when you put Q1 and Q2, you know what you did? This Q1 and Q2 started inducing charges in the surrounding medium. So this side they will spread out. So at infinity you will get positive. This Q2 also will put negative. So if you see there is a huge negative charge at the center, it will be non-uniform distribution. We can't figure out how it is. Now if you look at the forces between them, Q1, Q2 both will repel. So you will get K Q1 Q2 by R square. Remember, this is the same force that you have in vacuum. This value is not going to change. The problem is, it's not the problem between the charges, it is a problem with the induced charge. This induced charge started attracting them inwards. You're getting what happened? Because this induced charge is pulling you inside, the net force has changed. Now, the net force on a charge, it is not only the interaction between Q1 and Q2. So net force on the charge will be the force between the charges plus the force due to the induced charges. So when you put a medium, the surrounding region, you're inducing charges, and these guys are creating an additional force. And this we saw, this is nothing but F vacuum by epsilon r. And this is F vacuum. This is F induced. So from here, you can actually calculate the force due to the surrounding medium. So these induced charges create a force which is minus F vacuum into 1 minus 1 by epsilon r. This is also force due to the surrounding mediums. Quite a good result. And remember, this is valid only if the whole region is filled with medium. You just can't have little medium there. You have to fill the entire space with the medium there. If entire space is filled with medium. Quite a useful stuff. So this is the reason why the force decreases. Randomly it doesn't decrease. Let me give you one more example. What if you have plus Q1 and minus Q2? Now, how do you explain this? So it doesn't matter what charges you bring, force will always decrease. So plus plus I explained, minus minus also I can explain. What if one is plus and one is minus? Now what do you think will happen? The plus will induce a negative charge here. The minus will induce a positive charge here. They'll cancel out now. They'll start getting neutralized in the center. This plus will induce negative. This minus will induce positive. They induce opposite charges. So at the center, they'll get neutralized. But on the outside, now you'll get more positive here. You will get more negative here. You're getting what is happening? So between the charges will get neutralized, but now the charges are on the other side. Now this will attract, this will attract. K Q1 Q2 by R square is the force between the charges. Now the induced forces are outward. There, here also the force decreased. So it doesn't matter. You keep like charges, unlike charges, the force will always decrease. Is this clear, everyone? So the important statement is this. Force between charges doesn't depend on medium. Now be careful with the wording there. Let me write it on the next page. But have a look at this page. Force between charges won't depend on the medium. Force on each charge will depend on the medium. Is this page clear, everyone? But getting the reason why the force decreases, it is because of the induced charges in the medium. This doesn't happen in gravitation. Because in gravitation, if you put a mass in front of something, you don't induce masses, isn't it? That's what I said. Electrostatics is a much higher version of gravitation. In gravitation, you don't have induction, you don't have conduction, you don't have a friction, you don't have a lot of things. So, and it is only attraction every time. So this is the statement there. Force between charges is independent of medium. Whereas force on each charge, see, the words are completely different. When you say force on each charge, you're talking about the net force. Depends on the medium. I mean, think about it, kind of makes sense. Let's say you're standing there. I come and push you with 100 newtons. Some other person is coming and pushing with 20 newtons. Why will my force change because this guy is pushing? You get in the question? If I'm pushing you with 100, some other person is pushing with 20, why will my 100 newtons change because someone else is pushing you? What will change? Net force will change, isn't it? Net force will change, 100 minus 20. My force won't change because someone else is pushing you with 20. Are you getting the difference? So the two charges will still keep pushing each other with the same force. The difference is the induced force. So exam mein na, they'll ask a question like this. Let's say we have two charges, Q1, Q2, and let's say in vacuum, the force between them is F. Now what you did, you kept the whole system in a medium. If the charges are dipped in a medium whose relative permittivity is 5. So then the questions will be like this. What is the force between the charges after putting them in the medium? Force on each charge, force on charge due to the surrounding medium. This entire surrounding medium which you have, how much force is that exerting on this? There are three questions you can ask you. The problem, most people remember like this. If you put charges in a medium, force becomes F by 5. They really don't know which force you're talking about and why does it decrease. But there are three things I can ask you. What will be this? What's the force between the charges? It will be F only, right? If your force is F in vacuum, you keep a medium or no medium, force will be F only. What is the force on each charge? This is F by 5. Then what is the force due to the surrounding? The balance for F by 5. Is this making sense, everyone? The force between charges won't matter if you're in vacuum or if you're in a medium, it doesn't matter. Easy? Clear? Let's see a question. So remember, there are three types of forces they can ask you here. Did I get the numbering wrong? 4, 5, 6, 3, 2, 9, right only. Let's see. Last one for the day. We have two pendulums. Okay. The density of the ball is rho b. Charges plus q. This is also rho b. Charges plus q. We keep this in vacuum. Gravity is there. So both will repel each other. And yeah, this angle is 30 degrees and let's make it 60. Let's make it 60 degrees and 60 degrees. Then what you did, you took this whole setup and then you immersed this in a liquid. Then something happened and these two pendulums, remember length is L and L, they came closer. The angles became 30 degrees and 30 degrees. And this whole space is filled with a medium. Where rho L is the density of the liquid. Epsilon R is the relative permittivity or the dielectric constant. You're getting the whole scenario? Initially, the angles were 60. When you keep them in a liquid, the angles became 30. Find the density of the ball. Find rho b. So we have two pendulums in vacuum that repel each other and make 60 degrees each. Identical balls, same charge plus q. When you keep them in a liquid, something happens and suddenly the angle becomes 30. Using this data, find the density of the bobs. Answer will come in terms of rho L and epsilon R. So since they're in equilibrium, what you do? Start with an FBD. When you say something is at rest, start with an FBD, meaning indirectly that's the biggest hint telling you boss use NLM. Hmm. Try. I'll give you a minute more. Start with the free body diagram. Look at this. If I take this, what are the forces acting on this? We have tension, we have mg. Mg is nothing but density of the ball, volume of the body into g. And we have repulsion force here, which is kq square by r square. This distance will be r, which is 2l sine 60, which is L root 3. And this angle is given as 60 degrees. So from here we get tan 60 will be the opposite side, which is kq square by r square mg. Agreed, everyone. Tan theta will be opposite by hypotenuse center. Now, when you draw the FBD of this guy, now something happens here. The tension will be different, T dash. You'll have your weight mg, that is same. Now you'll also have a buoyant force FB, which is rho liquid volume g. You also have a buoyant force. On top of it, even this force will decrease now. This guy will be k q square by, this will be the new distance r dash, which is 2l sine 30, which is L. This will be r dash square by 1 by epsilon r. Is that making sense? The repulsion force will become 1 by epsilon r times. So two things happened. The distance changed. The force curve became 1 by epsilon r. And you're telling me now this angle is 30 degrees. So if you look at the net force on this, we'll have tension T dash. This force will be mg minus buoyant force. And this will be the new repulsion force, 1 by epsilon r k q square by r dash square. This angle is 30. So we have tan 30 will be kq square by epsilon r dash square by mg minus fp. Check. This is your equation 1 and this is your equation 2. If I got these two, my job's done. So two things happened when you kept it in a liquid. You introduced a buoyant force and you also introduced a medium, so the overall force decreased. Are these equations clear, everyone? Then you're done. You just divide them. Then we get tan 60 by tan 30. This will be kq square by r square mg. This guy will be kq square by epsilon r dash square mg minus fb. Kq square will cancel. You'll be left out with mg minus fb by r is how much? L root 3 ka square. So that will be 3l square. This will be mg. Epsilon r will go up and r dash square will be l square. Tan 60 by tan 30 is 3. L square will cancel. We'll have epsilon r. Mg will be rho body Vg minus rho liquid Vg by 3 into rho b Vg. Vg will cancel everywhere. We got 9 is equal to epsilon r rho body minus rho liquid by rho b. Yeah, and this will be 9 rho b epsilon r rho b minus epsilon r rho l. So we get rho b is equal to epsilon r rho l by epsilon r minus 9. Check. So for this question to satisfy, for this to exist, epsilon r must be 9. That itself would be another question. Find the minimum, dielectric constants for this situation to occur. Density can't be negative, so epsilon has to be 9. Now this is all just working, but did you guys get these two equations? There, if you got the two equations, then job's done. That is the main thing. Then it is just a matter of solving. Divide the two equations and just keep writing. Buoyant force is rho LVG and mg is rho BVG. Any doubts on the steps, everyone? There, electrostatics, fluid mechanics, and NLM. Clear with us? There. That is a little about forces. So next class, when we catch up on Thursday, we'll continue with something called field and potential due to point charges. That is also a pretty good one, field-based concepts. And then we will see field and potential due to continuous bodies. We'll be using a lot of integrations like the way we did in center mass and moment of inertia. Quite important. So the overall chapter is pretty good. Like that's what I'm saying. When you do this, gravitation actually becomes quite easy. Okay, so with that, we'll wrap up for the day, right? The test is online, so make sure to give till Sunday. And then, yeah, I think with that, we'll wrap up for the day. So SHM is over, so please start solving, finish off by this weekend, whatever pending you have. So any doubts in today's class? Anything else you can stay back and ask? Or